We looked at a linear inverse model approach to look at the MJO forecast skill dependence on weak and strong NAOs and so on. Linear inverse modeling is a statistical technique which looks at the lagged covariances between multivariate fields to see what is the best linear model that can capture the predictive relations based on the lead lags. Here we will look at a set of actual forecast models that were used to do experiments on MJO skill, MJO prediction skill based on the initialization in different phases of NAO and on the strength of the NAO. This is Harry Hendon and others involved in this paper that's just been accepted, I think. So here we are looking at error interim as the reality. It's a reanalysis product, and we are looking at frequency of MJOs based on the phase 1 to 8 and the NAO index of greater than 0.5 or less than minus 0.5, so positive and negative phases of the NAO. So you can see that there is clearly a dependence on the strength of the NAO for some of the phases, phase 2 and 3 here, and maybe 5 and 6, and you remember where the convection sits based on the phase of the MJO. So then we look for different models like Bureau of Metrology, Chinese model, and all these ECMWF, Japanese model, US model, UK Met Office model, and the others. And you can see that many of them do a reasonable capturing of many of them reasonably capture the skill of MJO phase relation with the NAO. We are looking at observed 21 to 30 day lagged occurrence frequency of MJO phases following positive and negative NAO in extended winters of 1981 to 2017. The rest of the panels are probability of occurrence of the MJO phases in the forecast period of 21 to 30 days initialized with the positive and negative NAO for individual S2S models, subseasonal to seasonal models. The vertical bars represent 95% confidence level from a 10,000 bootstrap resampling calculation. So the forecasts are made and then there is a statistical resampling done to capture the statistics of these confidence limits. Nonetheless, if you look at the physics again from ERA and whether the different models, forecast models, are capturing it, we are looking here at the difference of the U200, so 200 hectopascal zonal wind anomaly between positive and negative NAO composites averaged from 0 degree longitude to 90 degree east. So we are basically going over Africa into the central Indian region as a function of latitude on the horizontal axis and lead time on the vertical axis. The hatched areas indicate that the difference is statistically significant. So you can see here are the on the longitude we have the latitude. So you are going here from so South Pole to the North Pole, and you are looking at am I right? Yeah. No, minus 30 to the North Pole. Sorry, that's not minus 90. These figures tend to be so small that you have to blink at them, but even in the publication. So you clearly see the upper level winds with the lead time. So we are looking at the vertical axis is lead time going from about 0 penta, I think 0 lead to 5, 10 up to 30 days. So you can see the relation along the latitude, and in the northern hemisphere you see this strong persistence of the zonal wind anomaly at all lead times in the ERA interim, which is used as reality here, and the models looking at other structures that relate to how the extratropical signature is brought into the deep tropics to affect the MJO in the Indian Ocean sector and the African sector. Some models have a better skill than others, so you can see the persistence of this here, and the statistical significance is shown in these hatched areas. So what am I saying? Basically, we have looked at the potential feedback of the MJO onto the NAO and the phase change, and then the feedback from the NAO to the MJO. Now we are more specifically looking at the forecasts in the dynamic models that do MJO forecasts, as opposed to the limb model we looked at in the previous forecast. Looking here at the spatial distribution in the tropical region for the difference between positive and negative NAO composites of U200 anomaly in the forecast period of 21 to 30 days. Positive and negative values are plotted in red and blue colors respectively. The contour interval is 0.5 meter per second. Zero value is discarded, and then there are statistical significances implied in the shading. Okay, so here you are looking at era interim. So you can clearly see this relation between the NAO phases and the U200 zonal wind anomaly. Why we look at U200? Because that's where the extratropical signature is coming into the tropics, and the lower surface forcing, which we will see in the next plot, happens based on the convergence divergence anomalies typically induced in the upper atmosphere by the NAO, and how that induces a surface anomaly and convection and heating and waves and so on. So that's era interim. That's the Bureau of Meteorology in 21 to 30 days. CMA is not as well organized as in this model, for example, and this UK Met Office is doing fairly well. KMA, I think, is the Korean Meteorological Agency, and so on. So you can see the skill of the models is different out to several pentads, and you want to be able to make a forecast obviously out to several pentads for it to be called S2S forecast. This is looking now at the difference between positive and negative NAO composites of U850 anomaly. So now we are looking at the surface, and OLR anomaly, so the convection anomaly induced by the NAO phasing in the forecast period 21 to 30 day, as in the previous figure. Positive and negative values of U850 anomalies are plotted, and statistical significance is implied in the shading. So there is UK interim, era interim, and you can see the Indian Ocean region convection is affected. So positive OLR is in color. So we are looking at OLR anomaly. So the phase of the MJO that is affected is implied by the impact on the convection in the era interim versus the BOM model here versus the other model. So you obviously there are many details, because some model like CMA may be doing the convection anomaly and the low level influence okay, but somehow its response in the upper level may not be as coherent as the era interim or what is done in BOM, for example. So there are details which depend on how the dynamic connection between the upper level and the lower level is working, and how the convection response is probably different based on convective parameterization and other details, or land atmosphere interactions, ocean, whether it's a coupled model, SSD is prescribed, and so on and so forth. Many details will determine how the upper level and lower level responses are captured compared to era interim, and how that corresponds to the convection response, because ultimately you want the convection response, but you also obviously want the remote teleconnections of the MJO, which may be okay with dynamics being captured properly, but if convection heating is not there, then the waves are not there, so you have to make sure that the model is not capturing the dynamic response for the wrong reasons. So all kinds of complications can be there when you look at models. This is just looking at MJO skill in days. for all MJO events and strong NAO and weak NAO events, and you are looking at the lead time in days when the correlations drops below 0.5. The vertical bars represent 95% confidence level of confidence from 10,000 bootstrap resampling calculations. So the main point is confirmed from what Lim had confirmed statistically, and that is that the strong NAO has a higher skill at a longer lead time. In all the models tend to do that, but some model, for example the CNRM model, doesn't show much of a difference between strong and weak NAOs, and the ECCC model has generally a shorter lead time forecast skill. HMCR is the shortest lead time here, only out to a couple of weeks, which could still be useful if it's consistent skill. Of course, then people also look at multi-model ensembles to see if that improves the overall skill, but you can see here JMA and UK Met Office are not capturing the big difference between the NAO strength and MJO skill at all. So UK Met Office here is doing a reasonable job in the convection response and the upper and lower level dynamic response, but it doesn't seem to care about the about the strength of the NAO in its forecast skill. Okay, so one has to again worry about how the model skill is coming about independent of NAO, why the NAO MJO relation may be weaker or not as dependent on the strength of the NAO in some models, even though they may have good skill during both phases of the MJO, because other teleconnections like amount of water being brought in the atmospheric rivers could be different. European winter storms associated with MJOs may be not captured as well, and so on and so forth. So looking at the MJO skill is one thing, and then to look at its teleconnections on specific known events is another thing. Okay, so we will leave it here. Just gives you a good sense of how the tropical extratropical interactions are can be used in an engineering sense to advance MJO skill, intraseasonal variability predictions. Okay.